Welcome. We'll start off the material for exam 2 with section 2.3, higher order derivatives. So far, we've been finding first derivatives, y prime, or f prime of x, or dy dx, all equivalent notations. The first derivative tells us how the original function y, or f of x, changes, how that output changes when the input changes. If we take the derivative of a derivative, we get a second derivative, y double prime, or f double prime of x, or this fancier notation, d squared y over dx squared. Notice the squareds are not in the same place in that notation. And again, I will probably emphasize the prime notation. Again, I'm just saying y double prime, f double prime. And yes, we can continue to take derivatives and get even higher order derivatives. So here's something for the third derivative, f triple prime. And then it gets unwieldy to use primes, so we just say f up here with a little 4 in parentheses, the fourth derivative, the fifth derivative, etc. So let's try this. Example number 2, we're going to find the first derivative, f prime, the second derivative, f double prime, and then the third and the fourth derivatives for our function f of x equals x to the fifth minus x cubed plus x plus 6. I think I'll just do them right underneath, so it's kind of easy to see where things come from. I'm going to go straight into the derivatives. Hopefully you've practiced in 2.1 and 2.2, and you're comfortable without showing any thinking work. 5 comes down from x to the fifth. We're left with 5x to the fourth. In the middle, we'll have minus 3x squared. And then from the x, we just get a plus 1, and the 6 goes away entirely. That's our first derivative. Second derivative. The 4 comes down, times the 5 would be 20x cubed. Don't lose that new exponent. In the middle there, 2 comes down, we get minus 6x to the first power. I don't bother showing the 1. And now the 1 goes away. The third derivative, f triple prime of x, let's see, 3 comes down, we get 60x squared minus 6 from the 6x. And then lastly, our fourth derivative would be 120x, and the 6 goes away. So there are the first 4 derivatives for this function. And if you think down another step or two, you might realize, oh, this function eventually disappears and everything will be a 0 at some point. Is that always the case? No, as we'll see in our next example. But in this one, I think the sixth derivative is where we'd end up with a 0. So let's try another example, example number 8 out of our book. So here we just want the first and second derivatives because you might recall here with variables in the top and bottom, we're going to use the quotient rule. So let's get that written down. My writing's always a little messy each time until I get used to it. All right, so if we do have variables in the top and the bottom, so u over v, then we're going to go u prime times v minus u times v prime all over v squared. So let's get working on that for the first derivative. So let's see here. Can I go? Well, no, I'm going to write it out because it's my notes. So I'm going to take the derivative of the 3x minus 5. And again, you might be comfortable enough to skip this step. Okay, times the x minus 3x minus 5, and then the derivative of the x all over x squared. And so that will just be 3 times our x minus 3x squared. Oh no, sorry, that's, I have to take the derivative first. I started to distribute. Derivative of x is just 1. Well, that's nice. All over x squared. So let's see here. I think I'll just keep breaking down the page. 3x minus another 3x, those go away, and we get positive 5 over x squared. So there's our first derivative, and you might recall that we can rewrite that with a negative exponent which makes our second derivative super easy. Since there's not x's on the top and the bottom, I'm not going to use the quotient rule. You can, but realize the derivative of the 5 is a 0, and that just cancels out a whole bunch of the quotient rule. So you can use the quotient rule, it's just harder than we need to do. So then if we have just this rewritten first derivative, 5x to the negative 2, the second derivative is going to be, let's see, the negative 2 comes down and we get negative 10x to the negative 3. Oops, lost my x. And that's it. And of course you can rewrite it, f double prime of x equals negative 10 over x to the positive 3. All right, let's go a little further. Each derivative tells us how the previous level function is changing. Ultimately, though, we want to relate each derivative back to the original function. For example, the first derivative gives us the instantaneous slope of a function. It tells us whether the function is increasing or decreasing. Okay. What does the second derivative tell us about the function? It does tell us the first derivative is increasing or decreasing, but what does it say about the original function? The second derivative tells us how the change in the function is changing. If the function is already increasing, is it increasing faster and faster? Or is it increasing but slowing down? So think of the height of a river during a storm. When the rain is pouring down, the river might be rising faster and faster. Uh-oh. But as the rain starts to slow, the river will continue to rise, but not as quickly. So we'll see that rising start to slow down and hopefully start to diminish. If a function is already decreasing, is it decreasing faster and faster, like a snowball, or is it decreasing with a hope of possibly leveling off? Is it slowing down? Think of the population of bees. We know the number of bees in the world is decreasing. Is that number decreasing faster and faster, maybe signaling extinction? Or is the decrease slowing down, giving us hope that they will not disappear? Do you see how there are 4 possible things going on in the 2 scenarios, the storm, the river water, and the bees, in the 2 scenarios just described? A function can be increasing at an increasing rate or increasing at a decreasing rate. The function can be decreasing at an increasing rate or decreasing at a decreasing rate. And the pictures can really help. The language is tricky, and you just have to sort of sort it out for you. So again, the pictures might help. Increasing at an increasing rate. Increasing, but at a decreasing rate. And then decreasing at an increasing rate. And then lastly, decreasing, but at a decreasing rate. So using the derivatives, how do the derivatives help us with these pictures? When the first and second derivatives are the same sign, the function is changing at an increasing rate. So that's a key thought right there, when the first and second derivatives are the same sign. And then when the first and second derivatives have opposite signs, different signs, then the function is changing, increasing or decreasing, at a decreasing rate. So that's the key. So let's take a look at how that applies up above. So increasing functions have positive first derivative, all right, greater than 0. So both of my first graphs have a positive first derivative. Both of my second graphs have a negative first derivative because they're decreasing. And if we don't really know about the second derivative, but I can see that the description of the first graph was increasing at an increasing rate, this has the same sign second derivative. So the second derivative is also positive. So first derivative positive, second derivative positive, increasing at an increasing rate. In the second picture, we're increasing but at a decreasing rate. So if my first derivative is positive, I know that my second derivative is going to be negative. The opposite sign, different sign. In my third graph, because it's decreasing, the first derivative is negative, guaranteed. But because it's decreasing at an increasing rate, like a snowball, then the second derivative is the same sign. It's also negative. And when the first derivative is negative, but we're decreasing at a decreasing rate, it's getting less steep, then the second derivative has to be the opposite sign. So the second derivative would be positive. And again, super confusing, a lot to keep track of. I have to just draw my pictures every time and think it through. I'm going to stop there and we'll come back and try some examples of working with these ideas.